This is the third part of Errors and Uncertainties. We've done part number 1 and part number 2. The links of those videos are in the description. Now, part number 3, we're going to understand how to do these calculations of uncertainty, right? In terms of absolute error, in terms of percentage errors, in simply addition or subtraction quantities, multiplication or division quantities. So there are basically 4 functions or 4 arithmetic operations that you can perform on any calculation. And there is a 5th one in terms of the power. Let's see how it goes. Now, where can you find out or where can you see addition or subtraction or a case of addition or subtraction? But before we move ahead with that, we need to understand how to represent a quantity in terms of errors. Now, for example, you take this measurement, that is this one, let's say. It is an 8.8 centimeter single point. Now, since you're taking this measurement from, let's say, with the level of your eyes, even if you do avoid the parallax error, there is a high chance that either you have overestimated this value or you have underestimated this value. To include this, we add the least count in every measurement of that respective instrument. Now, how much error can there be because of this instrument that I'm using to measure this value, right? So this is called absolute error. Why do I call this absolute error? Because I know for a fact that it has the same unit, which means that from this value, it could either be 8.7, which is 0. less than 8.8, or the absolute worst could be 8.9, which is 0.1 more than 8.8, right? So this range is still being for centimeters, right? So this is absolute error because it has the same unit as the rest of the measurement. Now, if you do it this way, for example, if you divide 0.1 centimeters with the reading, which is 8.8, and multiply this with 100, whatever answer you get will be called the percentage uncertainty, right? So this is what he's going to talk about. What is the absolute error and what's the percentage uncertainty in the calculation or in the value. So right now we are familiar with these two terms. So let's move ahead with the calculations or with the formulas that are expected of us in these chapters. So first, let's look at subtraction. What do we mean by subtraction? It's possible that there is a function of, let's say, speed, distance, time, any formula in physics that requires you to subtract 2 values. Take this example as well. If you want to find the length of this lead pencil, the length of the lead pencil will be calculated as subtracting P2 from P1. So here you are using a subtraction function, right? Now, if there is an absolute error involved in the readings, how do you deal with that? Now, what you would have done, simply, there are going to be 2 steps for this. The first step deals with calculating the true value, or you can say the calculated answer. The second step deals with calculating the errors or the absolute errors in these readings, how to do them collectively. You see, you follow the function, which is of subtraction, but you use the value. So for the true value, for the correct answer, you will be using these numbers, which are the actual measurement. And what are you supposed to do with these numbers? You're supposed to subtract them, right? So this bracket goes away like this. So 8.8 minus 2.0. The next step is that you add the error, the sign of error or the absolute error or the error calculation in the middle like this. And then you deal with errors separately. How much error is there in the first reading that you're subtracting? That is 0.1. So 0.1. Plus how much error is in the second reading? That is 0.1. So 0.1. Notice that even if you're dealing with a function of subtraction or you're dealing with a function of addition, errors of both quantities will always be added together. I will get to this in the next example as well. So what's going to happen in the next step? So you subtract 8.8 from 2, you get 6.8 plus minus how much error is there? This is going to be 0.2. So error in addition and subtractor will always be added together. Now this is your answer. This is the answer for length. To represent this, this is what it's going to look like in terms of symbols. But this is the length L plus minus delta L. Now this delta L value is this 0.2, which represents the absolute error in 6.8, which means that the highest possible wrong answer we can get because of this is going to be 7.0, which we find by adding it into this. And the absolute low answer that we can get on the worst day, on a bad day, when everything is going wrong, is going to be 6.6 centimeters. There is a range of values, right? So this is our absolute error, 0.2 is absolute error, 6.8 is the true value. If I wanted to calculate the percentage error in this, what I simply would have done is the absolute error, which is 0.2 divided by 6.8 into 100. My answer would have given me a percentage uncertainty answer. Now, one more thing, if you were to write this down properly, this would have been length is equal to 6.8 plus minus 0.2 bracket close and centimeters, which is the common unit for this one and this one, right? Okay. Okay, moving on. This was a function for subtraction. Let's do something for addition. Now, in this situation, he asks you the length of the track, for example. What is the length of the path of the track? And for this example, of course, I'm ignoring this curved path length of this track. I'm just taking this as an L-shaped track in which I'm just going to be adding this 300 and 400 together. Okay. Now, for the sake of simplicity, for the sake of change, let's change this value of 2 to a value of 3. When you were measuring this, you had an error of 3. It's fine. So now if I want to find the length of track, what am I supposed to do naturally? I will be adding both of them. So length 1 plus length 2. Now, since I'm doing this in terms of addition, this becomes the addition function, right? Okay. So again, the examiner will not suggest that employ the technique of addition or employ the technique of subtraction. The examiner expects you to understand that what function are you performing in this calculation? How are you getting your answer? Are you getting your answer by subtraction? Are you getting your answer by addition? What are you doing? So whatever you're doing, this is how you're going to go about it. I'm using simple examples so that you understand how to solve them. Okay, so length of track, I'm supposed to do this. And again, I'm supposed to break it down into two problems. First, I will be using the true values. And in the second bracket, I will be dealing with the errors. So the first bracket goes something like this. So 400 plus 300. Why? Because there is a function of addition. Addition gets performed on the true values. Plus minus, what am I supposed to do with the errors? Errors in addition and subtraction function both or always will be added together. So this is going to be 3 plus 2. Notice over here we added errors together even though it was a subtraction function. So over here we are going to get a 700 plus minus 5 bracket close as meters. This is my length of path L. And this is my absolute error. This is my true value. If I wanted to find the percentage error or percentage uncertainty, this would have been 5, which is the absolute error, divided by the true value, which is 700, which I calculated, multiply with 100 to make it a percentage, right? So we understand how to deal with percentage errors. Now, it begs the question, why do we want to find the percentage error? Why do we want to do this? You see, the idea with percentage is that it has no unit. The units get cancelled out. If you are dealing with a situation in which there are more than one quantities which don't have the same unit, if you perform addition, subtraction, or multiplication, how do you deal with that? Now, for example, you were making an equation, let's say, although this is physics, in terms of physics, this is not possible. But for the sake of understanding, let's say that there is a quantity X which is being formulated, which is being confirmed, which is being made by this equation, in which there is a quantity P and there is a quantity, let's say, Q, by adding both of them. Now, the unit of quantity P is meters per second, but the unit of quantity Q is, let's say, amperes. Can you add them together? Again, I remind you, this is no equation. In terms of homogeneity, principle, this equation is entirely wrong. It's wrong, but for the sake of understanding, can you add them together, or can we add their errors together? No, we can't do that. So instead, what we do is we convert P into percentage error, we convert Q into percentage error, and then we can add them together because they're both now in terms of percentages. P would have had its own percentage, Q would have had its own percentage, and now they can be added together. So the end of the day, the goal of finding the percentage error is to make sure that the units don't get involved in the final calculation. Luckily for us, in addition and subtraction, the units remain the same, but that's not so simple in terms of cases of multiplication and division and the power rule. Let's move ahead with them. So now we come towards multiplication. Ignore the spellings over here. So now we move towards multiplication and division and power rule. How does that work? So I have one function in physics that is in terms of multiplication. We can do the same thing in terms of division by rearranging the equation in somewhat, let's say, R equals to V divided by I. We can go over with that as well. But let's only focus on the multiplication factor that is over here. And then for the power rule, we have another formula, which is I square R. How do you deal with that? How do you find the error in these calculations? Okay, so this is what we're going to learn from this part onwards. Let's first deal with multiplication. So for multiplication, he gives us the function that is v equals to IR. Notice it could have been anything. It could have been any function in physics. I'm choosing v equals to IR so that you can relate. This could have been any other function. For example, to find volume of a cube, you need length, breadth, and width. This is also a multiplication function. Now, examiner will not tell you that this is a multiplication function. You know this yourself. You're supposed to identify this yourself, right? So how to deal with this? We have a value of I and R. They have different values of uncertainties. Now notice, can we add their uncertainties together like we do in addition and subtraction? We can't do that. Why? Because their units are different. Because their units are different, we need to use the percentage uncertainty method. So for multiplication, division, and power rule, you will see that at the end of the day, the examiner would want you to calculate the percentage uncertainty. How to make the error function in this. Now, the error function looks something like this. We have a delta V or error in V divided by V, the actual answer of V equals to some delta I or change in I divided by the true value of I plus delta R divided by the true value of I. Where are the deltas? So the second values in both situations will be the deltas. These are our true values, which will be used for the calculation. Again, there will be two steps for this. So this is my error function for this particular problem. Okay. How to deal with this? So step one, or a simpler step, would be to first calculate the true value. Calculate the true value. Calculate the calculated answer. What do you get by multiplying I and R, which is 2.2 with 40? So first calculate V, which is going to be IR, which is going to be 2.2 into 40. So this comes out as 88 volts, right? Now this is my calculated answer, which is going to go at this place of the calculation. Now let's be done with it. This, my step one is complete. This will be my step two, in which I have to calculate the fractional or percentage uncertainty. How do you go about this? Now keep it as it is. This will be delta V by V. Let's keep it at that. But how do you solve delta I by I? Now this is delta I and this is I. So the error in I divided by the true value of I plus, it is always going to be a plus, 0.5, the error in ohms or resistance divided by 40, which is the true value of resistance. Okay. Now this was a multiplication function, so we are going to go towards the percentage uncertainty. So delta V divided by, we can replace this V with the true value 88. So this remains 88 equals to, out. Now you solve this and see what happens. So this comes out as 0.0579. So 0.0579, right? And when you take this, now this is percentage uncertainty. If you just multiply this number with 100, this will give you percentage uncertainty, which is going to be 5.79. Now, since errors are always to one significant figure, this is going to become 6%. Okay. But for the sake of example, let's leave it at now. So let's keep this number and not multiply this with 100, because we've already found the percent. This is the route we take for percentage uncertainty. Okay. But this is the route we take for absolute uncertainty. You don't multiply this with 100, but instead take this 88 or calculated answer to the other side. So this is going to become delta V equals to 0.0579 multiplied by 88. Now when you do that, you're going to get 0.0579 multiplied by 88 is 5.0925. So this is going to be 5.0925. So what is my final answer for V? So V is going to be equal to the calculated answer, which is 88. So let's write this down first. Plus minus the absolute error is 5 only, because errors will always be up to one significant figure. So this is my final answer for voltage. And if I had to write this down the other way around in terms of percentage error, then I could have written it like this. So 88 volts plus minus 6%. Notice that volts, since the absolute error and the value itself have the same unit, I can do it this way. But since percentage has no unit, volts has to be added with 88, and I have to write down the percentage error separately. Okay, so there are two representations for this. You will do exactly the same thing, exactly the same process every single time, even if the question was for division. For example, you had a function, let's say that is z equals to x divided by y. Let's say this is the function. The error function would be delta z divided by, or the error in z divided by z equals to, who's responsible for the error in z? X and y, because they're being used in the calculations. So this will be delta x divided by x plus delta y divided by y. There will always be an addition. What are we trying to do? This is basically a percentage error. So this, after being multiplied with 100, 100 multiplies with this, 100 multiplies with this. What are you trying to find out? We're trying to find out the percentage uncertainty contribution by x and percentage uncertainty contribution by y. What are these two doing, or what have these two done to z, or calculated answer of z? It goes the same way, right? Okay, moving on. We have tackled multiplication, we've tackled division. Let's deal with power rule. So power rule, we have I square r, right? It can get more complicated than that. Of course, there could be a function of under root, a function of cube root. You should be prepared for that, but we're dealing with a simple example, and then we're going to move ahead. So power is equal to I square r. How to make the error function? Now that will be simply delta p divided by p equals to delta I divided by I plus delta r divided by r. Now, what do we do with the power function? What do we do with I square? Now, the rule is to multiply the power with the respective error function. If it had been an under root, let's say it was under root I, what would I have done? Simply delta I divided by I multiplied by 1 over 2, because the power of under root is 1 over 2. If this would have been a cube, then this would have been multiplied by 3, right? So whatever power that variable has, you're going to multiply this. Now, we understand this, that how does that function? Why do we do that? Why is this being multiplied? You see, if I write this number down as I multiply by R, there's nothing wrong with it, because I know I multiply by I is going to become I squared. If I were to write down the error function for this would have become delta I by I plus delta I by I plus delta R by R. Instead of going the long way, we developed a shortcut that since this is going to come twice, let's make it simple and just add the power towards the other side. Right, this is where the power rule comes from. So now to solve this, again, the method is going to be simple. First, we find out the calculated power, which is P I square R. The value of I given in the question is 2.2. R is 40. So this is going to be 2.2 square multiplied by 40. Let's calculate this. So 2.2 square multiplied with 40 gives us 193.6 watts of power. Okay, so we are done with this section of the question. We have calculated this. Now, how to deal with the error function? Let's move ahead. The same method that we've done before, we're going to follow that again. So first, we put in the values of the error in I. So 2, because of the power. The problem in I, or the error in I, is 0.1 divided by 2.2. Again, the same thing, 0.2.2 plus 0.5 divided by 40. And that is this one. Okay, now since we've done that before, okay, but since of course we didn't do it with the value of 2, let's do that and see what answer do we get. So this time around, this is 0.1034, which is equal to delta p divided by the calculated answer, which is 193, so 193.6. Again, I remind you, I can take two routes from here. I can simply just multiply this with 100, and it will give me 10.34% error, which will be rounded to 10% up to one significant figure, right? But if I want to find the absolute error, then I am going to avoid this route and go towards this calculation, that this p is going to go towards this side. So delta p divided by 193.6 equals to 0.1034 brought over here. So delta p is equal to, simply multiply them together. So multiply this with 0.1034, which is exactly 20. Okay, up to one decimal place. Yeah. So how do I write this down? So my error in p is 20. My calculated answer is 193. So I can write this down in two ways. So p is equal to 193.6 plus minus 20 watts. Now I know that this is absolute error, so watts goes with this and watts goes with this as well. The other option I have is P equals to 193.6 watts plus minus 10%. 10%. The other two options. Now, what would happen if you calculate the 10% of 193? You will get 20 back again. So all these errors and things are interconnected. Okay. So you can go to the percentage error route, or you can calculate the absolute error. Now, percentage error benefit would be if this power formula, if this power is a part of another formula, is a part of another equation, then we don't have to calculate everything again. We can just simply take the error in P or the error in power as a percentage error, and it will be easy to solve the question. Let's see how that goes in terms of questions and manipulations. Okay. So first he says, this is a question, he says that he has calculated the density. He's given you the mass, length, breadth, and height. We're going to use them to calculate the volume, and we already have a mass. He says uncertainty in the result. Now, he doesn't mention whether this is absolute uncertainty, whether this is a percentage uncertainty. Do we see a percentage sign in the options? No, we don't, which means that this is an absolute uncertainty because the unit of the calculation and the options is exactly the same. So how are we going to go about this? We don't need to calculate the value by using the formula density is equal to mass over volume. We don't need to do that. Instead, what we can do is simply calculate the error in D, which is what he was looking for. So the formula goes something like this. The error function is going to go delta D divided by the density is equal to change in mass divided by mass plus change in length divided by length plus change in breadth divided by breadth plus change in height divided by height. All right. This D has already been calculated for me, which is 2.5. So let's replace D as 2.5. He's already done that for me, right? So the first step is done. How do I go about this? Now, all of these things will be the deltas. These are the true values. So for mass, I'm going to go with this. So this is going to be 0.1 divided by 25 plus 0.01 divided by 5 plus 0.01 divided by 2 plus 0.01 divided by 1, right? Which is still equal to delta D divided by 2.5. Now, since I'm looking for an absolute error, what am I supposed to do? If I were to multiply this whole bracket with 100, I would have gotten percentage error. But I don't need that. So I'm not going to do that. Instead, I'm going to bring this number over to the other side and multiply it with this one. Be careful. You do this with fraction on your calculator. Just make sure that you don't miss out any numbers, and remember that all of these are going to be added together. Once you do that, your delta D is going to come out as 0.0525 grams per centimeter cube. It's very obvious that the option because of this 0.0525 is going to be option C. But we need to remind one more thing, that the error is always up to one significant figure. So that is why this has been rounded off to one significant figure, right? The correct answer for this option is option C. Similarly on this question, okay, so there was no question before. Okay, so again, this question is related to the uncertainty to calculate the speed. Now, what is the formula for speed? Speed is equal to distance over time. Do we have a distance? Yes, we do. Do we have time? Yes, we do. So there is a distance and there is a time. There are errors associated with these values. He says, give out the answer, with the true value, and its uncertainty in the value. Okay. Is this absolute uncertainty? Yes, because both of them have the same unit. There is no percentage involved. Okay, let's move ahead. So the first step is calculate the true answer. So this is going to be speed equals to distance over time using the true value, which is 40 divided by 2.5. So this is going to be 40 divided by 2.5. This gives me the answer as 16. But notice how many significant figures are there in the data. So there are 3 significant figures over here, 3 significant figures over here. So it's my choice, according to P3, according to the practical standpoint, how many significant figures can I say or can I suggest? We have to remain equal to the number of significant figures of the question or the data, or suggest one more. Okay, so we follow the minimum one and then suggest one more. So for example, if this had been a 2 significant figure number, so you're dividing, let's say, a 3 significant number with a 2 significant number, right? So the final answer will follow the smallest one. Ideally, it should be rounded off to 2 significant figures, but you can go up to one more. Similarly, if you were dealing with multiplication, let's say you were multiplying a 5 significant number with a 3 significant number, the final answer ideally should be good enough to 3 significant numbers. But in physics, it's allowed to go one more. So your answer could be 3 significant figures or 4 significant figures, right? So based on this idea, my answer should be 3 significant figures. So I am going to reject option A and D altogether because they're representing the calculated answer significant figures incorrectly. It's going to be a 2 significant figure. Okay, this was my step 1. Now step 2 follows the delta function or the error function. How much error do we have? So this is going to be delta D divided by D plus delta T divided by T, which will be a 0.1 divided by 40 plus 0.05 divided by 2.5. Now all of this is equal to delta speed is equal to speed divided by speed. What's the speed? That is 16. So let's take 16 over there. So this is going to become 0.1 divided by 40 plus 0.05 divided by 2.5 multiplied by 16. The answer is going to be 0.36 meters per second. But you already rejected that option. What are we going to do now? Remember, errors are up to 1 significant figure. So you deliberately round this off to 1 significant figure, which is 0.4, which is going to be this one. So option C is the correct answer for this question. Question number 5. Notice that every value is given as a percentage uncertainty, although they represent different quantities. For example, this is mass, this is acceleration, distance and time. Now, since they represent different quantities, can you add their errors together? No, you can't do that, but you can add their percentage errors together, right? That is why there is utility. That is why there is a need for percentage error. Now he says that the power used in acceleration of mass is equal to the product of force and velocity. So a formula for power, which is equal to mass into velocity. Okay, fine. Force into velocity. This is going to be like this. He says that there is a mass m. He defines every variable he's using. So acceleration is a, there is a distance s and time t. He says find the uncertainty in the average power. Now, what am I supposed to do with this? Can I replace these values? So I remember that from second law, F is equal to ma. What about velocity? So there is a distance, there is a time. So I can write down s divided by t in place of velocity. My formula is complete. Now notice that there is some multiplication and there is some division. Now when there is multiplication or division, we employ the percentage uncertainty function. What is that going to look like? So that will look something like this. So we are dealing with power. So this is going to be delta P divided by P equals to change in mass divided by mass, change in acceleration divided by acceleration, change in speed divided by speed, change in time divided by time. Do we need to do that again? Do we need to solve them? Are there any values given? So if you multiply this with 100, you get percentage uncertainty. Luckily, what he has done for us is that he's given that for everyone. He's given that percentage for mass, acceleration, speed, and time. So since this 100 is being multiplied with every single number, what are we left with? We are left with 0.1% in this whole bracket, plus for acceleration we have 1%. For speed we have given 1.5%, or we are given 1.5. For time we are given 0.5%. When you add all of them together, your answer is going to come out as 3.1%, which is option C, right? So moving on to the next question. That is why you can see it's very easy to add percentages. That is why everything is converted into percentages, even though they have different units. Now he says that he uses a caliper to measure the sides of the cube and he wants to find out the volume. Now, how do you find volume? Now, notice that examiner does not give you the formula. So volume is calculated by length, breadth, and width or height, whatever you choose, whatever formula you choose. And every side has 30 meters or 30 millimeters. What's the percentage uncertainty? First, let's make the error function. So delta volume or change in volume is equal to, or divided by volume is equal to change in length divided by length plus change in breadth divided by breadth plus change in width divided by width. Now, luckily for us, every calculation, every side has come out as 30 with an error of 0.1. So this is going to become 0.1 divided by 30 plus 0.1 divided by 30 plus 0.1 divided by 30. Since we are required to find the percentage uncertainty, I'm going to multiply this error function with the 100. And when you do that, you're going to find your answer as 1%. or 0.9999% if you calculate them manually first and then later multiply with 100, right? So this is percentage for this question. Question number 4, interesting question. There is multiplication, division, and then there is a power rule. When all of them are going to come together, it becomes even more simpler. So delta y divided by y, although this function is not required, but I'm writing this down anyway for your practice. Delta p divided by p plus delta x divided by x plus delta q divided by q. Have I done q correctly? No. Q is squared, so this is going to be a power of 2 or being multiplied with 2. Now, when you multiply this whole bracket with 100 to get percentage error, do I need to do that again? No, we don't need to do that because percentages are already given. Delta p divided by p and then being multiplied with 100 is going to be 6%. So this is 6%. This multiplied with 100 is actually 2%. Then plus, then q has an error of 4%, but there is a multiplication of 2. This becomes 8%. So 6 plus 2 is 8, 8 plus 8 is 16. So this is going to be 16% of error, which is option C. Question number 4. In this question, you may not know the formula if you're watching this in the beginning years of your A-levels. He wants you to find out the error in Young modulus. So the formula for Young modulus is stress over strain. When you simplify that, it becomes force multiplied by length divided by cross-sectional area into the extension. So I've simplified this as FL divided by AE. Now, do we understand force and other variables in this table? Do we find them? Yes. So force is Newton, so this is load. Length is this over here, right? Extension is this, E over here as extension. But we wanted to find out the area, but we don't have it. So what are we supposed to do? Instead of area is given as a diameter, so we added an extra step. Now, since we're dealing with a wire, which is circular, so the area of a wire or circle is pi r square. But since this is diameter, diameters are d by 2. Diameters are d by 2. So this becomes pi d by 2 whole square, which is going to become pi d squared divided by 4. Now pi is a constant and 4 is a constant. Do they participate in the errors? No, they don't, because we definitely know that one of them is pi and one of them is 4. We know their values definitely. So I don't need to include them in the error calculation. So the error function of my area of the area is proportional to d square. So in place of cross-sectional area, I can replace the error of d square. So the formula goes something like this: FL divided by d square E. The function becomes delta F by F plus delta L by L plus delta D by D plus delta E by E. Have I done some mistake? Yes. It's a d square, so it should be multiplied with 2 according to the power rule. So he has already given us the percentage errors of everyone. So force is 2% plus length is 0.2%. So this is 0.2% plus the diameter error is 1.5, but multiplied with 2, this is going to become 3%. And then we have delta E by E. So E has an error of 1%. When you add all of them together, this is going to come out as 6.2%, which is option